Hi everyone, welcome back to Chapter 5, Protein Function. In this lecture, we are going to look at part 2 of this chapter. And in this part, we are going to look at the applications of protein ligand binding. For this purpose, we'll be looking at two different proteins, myoglobin and hemoglobin, and how these proteins function. Let us consider a simple biological problem. Oxygen transport in the body. We all know that oxygen is a gas. Now, oxygen is poorly soluble in aqueous solutions and cannot be carried to tissues in sufficient quantity if it is simply dissolved in blood serum. Also, diffusion of oxygen through tissues is ineffective over distances greater than a few millimeters. Wow. So, how does nature get around this problem? And it is done so cleverly by using proteins that bind oxygen. But hey, the problem is not that easy to solve. Now, the first issue the nature has to take care of is this, that protein side chains or amino acid side chains in protein lack affinity for oxygen. There are some transition metals that bind oxygen well, but they would generate free radicals if they are free in solution. Again, you don't want free radicals roaming around in the blood. It's potentially dangerous. Organometallic compounds such as heme are more suitable. But iron 2 plus in free heme could get oxidized to iron 3 plus. That is again one of the most pressing problems because iron 2 plus is the metal that binds oxygen. And you want iron to be in Fe2 plus state. So the biological solution is capture the oxygen molecule with heme that is protein bound. Wow, that's an excellent solution that nature finds in this case. Two different proteins, myoglobin and hemoglobin, can bind oxygen. While myoglobin stores oxygen, hemoglobin transports them. Transport oxygen. Both these proteins, myoglobin and hemoglobin, function by using a protein-bound heme. Let us see as to what a heme molecule is. Heme consists of a complex organic ring structure, and this is called as protoporphyrin, to which is bound a single iron atom in its ferrous state. This is Fe2 plus state. Porphyrins, of which protoporphyrin 9 that is shown here is just one example. Consists of 4 pyrrole rings, 1, 2, 3, 4, and each of these are pyrrole rings, and they are linked by methylene bridges, as you can see, right? With substitutions at one or more of the positions denoted X, and structure B is the ones with substitutions. Now, this is the kind of a porphyrin structure that both myoglobin and hemoglobin binds. The iron atom that is in the center has 6 coordination bonds, 4 to nitrogens, 1, 2, 3, 4. 4 to nitrogen atoms that are part of the flat porphyrin ring, and 2 perpendicular to the porphyrin. As you can see here, that 2 of them are perpendicular, one on top, one on bottom, and the flat ring is from the porphyrin itself. The coordinated nitrogen atoms help prevent conversion of the heme ion Fe2 plus to Fe3+, that is from ferrous to ferric. Iron in the ferrous state binds oxygen reversibly, whereas the iron 3+ state does not bind oxygen. Heme is found in many oxygen transporting proteins as well as in some proteins such as cytochromes that participate in oxidation reduction reactions. In order for oxygen and heme to bind, the protein structure must allow it to happen. In globins, for example myoglobin, one of these two coordination bonds is occupied by the side chain of a proximal histidine residue. The other is the binding site for molecular oxygen. The coordination positions the heme in space, which then allows optimal interactions with oxygen. Now, when oxygen binds, the electronic properties of heme ion changes. For this ion, the property changes when the oxygen binds. Now, this accounts for the change in color from dark purple of oxygen depleted venous blood to the bright red of oxygen-rich arterial blood. Right? If you look at arteries, the blood vessels are rich in oxygen, so the color is bright red. Whereas if you look at veins, the color is dark purple because the blood is depleted of oxygen. And that has to do with the properties of this ion that is bound to the heme and the histidine. Oxygen binding to myoglobin follows a hyperbolic pattern. As we have seen before, the binding of a ligand to a protein also follows a hyperbolic path. Now, because oxygen is a gas, we must take some minor adjustment to the equations that we have seen before. Right? Theta, as we saw before, the total number of sites occupied, which is equal to the concentration of the ligand divided by Kd plus the concentration of the ligand. Now, if we substitute L with O2, right, now if we take theta is equal to concentration of O2 divided by Kd plus concentration of O2. Now we can say that as any ligand, Kd equals the O2 at which half of the available ligand binding sites are occupied, right? So this is the Kd in this case. So we can easily convert the equation to O2 divided by O2 at 0.5 plus O2, right? In experiments that use oxygen as a ligand, it is the partial pressure of oxygen, or PO2. PO2 in the gas phase is what is varied. This is easier to measure because the concentration of oxygen dissolved in the solution is difficult to quantitate. The concentration of a volatile substance in solution is always proportional to the local partial pressure of the gas. So if we define the partial pressure of oxygen at O2.5 as P50, so this equation directly becomes this equation. So the concentration of O2 becomes PO2, and the concentration of O2 at half or 0.5 becomes P50. So the equation for a partial pressure of oxygen binding to globins, both myoglobin and hemoglobin, becomes theta is equal to PO2 divided by P50 plus PO2. And this is the equation that we will be using if we are considering oxygen as a ligand binding to a protein. Let us consider some spectroscopic properties of oxygen binding to globins. And this is useful when it comes to detection of oxygen binding to globins. The heme group is a strong chromophore that absorbs both in ultraviolet and visible range. Ferrous form, or Fe2+, without oxygen has an intense absorbance at 429 nanometers. Whereas oxygen binding alters the electronic properties of the heme and shifts the absorbance bands to 414 nanometers. Binding of oxygen can be monitored by UV visible spectrophotometry. Deoxyhemoglobin in venous blood appears purplish in color, whereas oxyhemoglobin in arterial blood is red in color. The binding of a ligand to a protein is rarely as simple as it is observed. The interaction between a ligand and a protein is greatly affected by the protein structure and often accompanied by conformational changes. For example, the specificity with which heme, which is this protoporphyrin molecules with the iron, the specificity of this that binds to various ligands is altered when heme is a component of a protein like myoglobin. For example, free heme molecules bind carbon monoxide, CO, at least 20,000 times better than oxygen. So the KD for carbon monoxide is 20,000 times lower than oxygen for free heme. But when the heme is bound to a protein, it is only about 40 times better than oxygen when the heme is bound to myoglobin. So how does this happen? When heme is bound to myoglobin, its affinity for oxygen is selectively increased by the presence of distal histidines, which is histidine E7. The FeO2 complex, now this is the example in a heme, the FeO2 complex formed by heme in myoglobin is much more polar than FeCO complex because there's a partial negative charge distributed across the oxygen atoms in bound oxygen that is bound to the heme due to partial oxidation of the interacting ion. Remember, Fe2 plus is the oxidation state of ion in heme that is bound to myoglobin. But there is a partial oxidation of iron. As a result, there is a partial negative charge in oxygen. And so a hydrogen bond is formed between the imidazole side chain of histidine E7, that is a distal histidine, and bound oxygen. And this stabilizes the polar complex electrostatically. And hence, the affinity of myoglobin for oxygen is selectively increased by a factor of 500 times. So now the heme in protein binds oxygen 500 times better as compared to heme that is not bound to a protein. And the fact that proteins such as myoglobin keeps heme buried inside its structure makes it much more easier for it to select oxygen versus carbon monoxide. And that is how proteins like hemoglobin and myoglobin selectively chooses oxygen as a ligand and prevent carbon monoxide generated from heme catabolism. Now, carbon monoxide poisoning is also a risk. If the carbon monoxide concentration goes up, carbon monoxide is always preferred as a ligand that binds to a heme. So that is exactly why CO poisoning is deadly. Nearly all the oxygen carried by whole blood in animals is bound and transported by hemoglobin in erythrocytes or red blood cells. Hemoglobin is a tetrameric protein consisting of two alpha chains, alpha 1 and alpha 2, and two beta chains, beta 1 and beta 2, each containing one heme group. So alpha 1 has a heme group, beta 1 has a heme group, alpha 2 has, and beta 2 has. Now, although fewer than half of the amino acid residues are identical in the polypeptide sequence of the alpha and beta subunits, the three-dimensional structure of the two types of subunit are very similar, alpha and beta. Also, the structures are very similar to that of myoglobin. So this is a beta subunit of hemoglobin, and this is the structure of a myoglobin. The way the heme molecule is bound in both myoglobin and hemoglobin is also quite similar. There are only 27 identical positions among these two proteins. X-ray analysis of hemoglobin has revealed two major conformations of this protein: the R state or relaxed state and T state or tense state. R state has very high affinity for oxygen, which means the Kd is very small. The T state has lower affinity for oxygen, which means the Kd is higher. Although oxygen binds to hemoglobin in either state, it has a significantly higher affinity for the R state, as I said. When the oxygen is absent, experimentally the T state is more stable and is thus the predominant conformation of deoxyhemoglobin. T state is related to deoxyhemoglobin. Also, hemoglobin readily undergoes conformational shift upon oxygen binding, and oxygen binding induces changes in the individual subunits and affects the quaternary structure. Now, the binding of oxygen to a hemoglobin subunit, either alpha or beta, in the T state triggers a change in conformation to the R state. When the entire protein undergoes this transition from T state to R state, the structure of the individual subunits, either alpha or beta, change little, but the alpha beta subunit pair together slide past each other and rotate. As you can see here, there is slight differences because the alpha beta pair rotate. In this process, there are some ion pairs that stabilize the T state are broken and some new ones are formed. For example, if you look closely at this structure, there is a histidine here which forms an ion pair or electrostatic interaction with an aspartate. Now these two are both from the same subunit. Now as the T state goes to R state, there is a rotation as this two subunits slide past each other, and this histidine now has come here. So that's the histidine HC3 has come here, and this has resulted in breaking of electrostatic interactions. Another important point is that in the T state, the porphyrin or the heme is slightly puckered, which means that it is not planar. This causes the heme ion to protrude somewhat on the proximal His. Remember the proximal His, that is one of the coordination site of the perpendicular ion. The binding of oxygen causes this heme to assume a more planar conformation, shifting the position of the proximal His, and this results in the R state. For effective transport of oxygen, hemoglobin must bind oxygen cooperatively. This means that the affinity for oxygen must vary with the partial pressure. Now, in lungs, the partial pressure for oxygen is 13 kilopascals, whereas in tissues, it's about 4 kilopascals. Myoglobin or any other protein that binds oxygen with a hyperbolic binding curve like this, as shown here, would not be well suited for this function, because a protein that bound oxygen with high affinity would bind it effectively in the lungs, but would not bind it effectively or would not release much of it in the tissues. If the protein bound oxygen with a sufficiently low affinity to release it in the tissues, it would not pick up much oxygen in lungs. Let me explain it clearly. Now, myoglobin is a protein that can store oxygen, not transport. Now, if myoglobin binds oxygen with high affinity in lungs, which means that it cannot release it in tissues. Now, if myoglobin were to have a very low affinity so that it releases in tissues, it would not be able to pick up oxygen from lungs. So, to do this function, hemoglobin is the best protein. Now, hemoglobin solves this problem by undergoing a T to R transition, as we saw before. And as more oxygen molecules bind, the R state becomes much more prominent and has high affinity for oxygen. Now, as you can see, a sigmoidal curve that is shown here, the S-shaped curve, is characteristic of hemoglobin. A single subunit protein like myoglobin will not have this kind of binding curve. That is because each molecule of oxygen binds independently to each subunit and cannot affect ligand binding to another molecule. Whereas in hemoglobin, for example, now if you consider hemoglobin as 2 alpha and 2 beta subunits, right? Now, if oxygen binds to this heme in this subunit, let's say this is alpha 1, this is beta 1, this is beta 2, and this is alpha 2. Now let's say it binds to alpha 2 first, right? Now, if this binds to alpha 2, now this is binding to a T state where there is no oxygen or deoxyhemoglobin. Now, because it binds to a T state, its binding is weak, but it leads to conformational change that are communicated to the adjacent subunit. So when an oxygen binds, what could happen is a conformational change. It changes the conformation of the protein. At the same time, another oxygen binds here. So oxygen binds here, then an oxygen binds to the next subunit, so alpha, beta, and then it binds to another alpha subunit here. So it can change the conformation there as well. And so all T states become R state, and this is all oxygen bound. And this periodic binding of oxygen is what is called as a cooperative binding, which means that binding of oxygen to one state affects the subunit next to the subunit that the oxygen is bound, and it changes the conformation and makes it much more susceptible to bind more oxygen atoms. So, summarizing what I just said, it must be a protein with multiple binding sites that has to bind oxygen if it were to effectively transport oxygen from one part of the body to another. Binding sites must be able to interact with each other, like hemoglobin. And this phenomenon is called as cooperativity. Positive cooperativity, which means first binding event increases affinity at remaining sites. This is recognized by sigmoidal binding curves. Negative cooperativity means first binding event reduces affinity at remaining sites. An allosteric protein is one in which the binding of a ligand to one site of the protein affects the binding properties of another site on the same protein. Now, cooperative conformational changes depend on variations in the structural stability of different parts of a protein. Consider an example here. The binding site of an allosteric protein typically consists of stable segments in proximity to relative unstable segments, with the latter capable of frequent changes in conformation or intrinsic disorder. Now, only an allosteric protein will have cooperative conformational changes. Now, in this protein, there are two subunits that are interacting with each other. This could be alpha, beta. In this case, no ligand is attached to this protein. There are three different regions. One is a stable region in blue, less stable region in green, and unstable region in pink. The moment a ligand binds to this binding site, which is shown here, some of the green regions become blue, which means that the unstable region, the less stable regions become stable, and then there will be some less stable regions, but that interacts with the ligand. Now, binding of a ligand to one site forces the binding of the next site to bind another ligand. So the second ligand molecule bonds to the second subunit, and the binding occurs with higher affinity than binding of the first molecule. This gives rise to positive cooperativity, which means that binding of the ligand to one site increases the binding of ligand to the next site.